Hello, higher physicists, and today we're going to look at the electricity questions from the 2019 Higher Physics paper. So, let's make a start. Question 12. A student sets up the circuit shown. When switch S is open, the reading on the voltmeter is 1.5 volts. Switch S is now closed. The reading on the voltmeter is now 1.3 volts, and the reading on the ammeter is 0.88 amps. State the EMF E of the cell. So what we need to understand here is that when no current is flowing, the voltmeter will read the EMF. As soon as current starts to flow, voltage will be dropped across the internal resistance, and so the voltmeter will read the terminal potential difference, the lower voltage. So our EMF here is the larger voltage, 1.3 volts. And we can write this on our diagram. This is always a useful thing to do. So 1.3 volts is the EMF. The terminal potential difference displayed on the voltmeter when the switch is closed is 1.3 volts, and the current 0.88 amps. Part 2, calculate the internal resistance R of the cell. So we just wrote these things on our diagram there. And we have this formula in our datasheet, E equals V plus IR, where little r is the internal resistance. So we can just place these numbers into that formula, E being 1.5, V, the terminal potential difference, being 1.3, and I being 0.88 amps. Rearrange it a little bit, and we get a value for the internal resistance as 0.23 ohms. Part 3, explain why the reading on the voltmeter decreases when the switch is closed. Well, as I just mentioned, what happens is, as the switch is closed, in this diagram here, when the switch is closed, the current will start to flow around the circuit. When current starts to flow around the circuit, charge has to be leaving the battery effectively, and energy is used up in getting that current out of the battery. So energy or voltage is dropped across the internal resistance. Part B, a battery of EMF 9 volts and internal resistance 1.2 ohms is connected in series with a lamp. The lamp has a resistance of 2.4 ohms. Determine the current in the lamp. So what are these values? Well, if we look at this, the 9 volts is our EMF. The 1.2 ohms is our internal resistance, small r. And the 2.4 ohms for the lamp is the load resistance or the circuit resistance. Now, in our normal internal resistance formula, we have E equals V plus I little r. Here, we're trying to find out the current, but as we don't know V, we can't use that formula. But we can expand that formula a little bit to make it a bit more useful. And we need to remember that V, the terminal potential difference, is the current multiplied by the circuit resistance, I big R. So we replace the V by the I big R, current multiplied by the load resistance. And in that formula, we can now take out a common factor of I, because we've got I times big R and I times small r. So we take out the common factor of I, and we get E equals I multiplied by big R plus little r. And that now gives us a formula in the form that we can actually use here. So E equals I big R plus little r. Insert the numbers that we have there. E is 9 volts. The load resistance is 2.4 ohms, and the internal resistance 1.2 ohms. And we can work out the current, 9 divided by, as it will be, 3.6, which is 2.5 amps. Part 2, calculate the power dissipated in the lamp. Now, we know the current flowing through the lamp, and we now know the resistance of the lamp. So the power dissipated in the lamp, we can use the formula P equal to I squared R. 2.5 squared times 2.4, 15 watts. Question number 13. A student investigates the charging of a capacitor. The student sets up the circuit as shown using a 47 microfarad capacitor. The capacitor is initially uncharged. The switch S is now closed. A laptop connected to the interface displays a graph of current against time as the capacitor charges. The variable voltage supply is set at 6 volts. Calculate the maximum charge stored by the capacitor. So the formula we have in our datasheet is C equals Q divided by V. I usually write it as Q equals CV. I don't know. I think that's how I learned it when I was a schoolboy myself. And we're trying to work out the charge here. So it's going to be the capacitance multiplied by the voltage across the capacitor when it's fully charged, which is equal to the supply voltage, which is 6 volts in this case. So we can put those numbers into our formula and work out the answer. 2.8 times 10 to the power minus 4 coulombs. B, the graph shows how the current I varies with time t as the capacitor charges. Switch S is opened and the capacitor is discharged. The resistor is now replaced with one that has a greater resistance. Switch S is again closed and the capacitor charges. Add a line to the graph above to show how the current now varies with time as the capacitor charges. Well, we want it to look a bit like this. The reason it looks like this is because using a greater resistance means less current will flow. So the initial charging current will be smaller. Also, because the current is smaller, it will take longer for the capacitor to charge. If we imagine we have a bath or a sink, and we put the tap on very gradually, then it will take a long time for the bath to fill. So the smaller the current, the longer it takes the capacitor to fill. If you turn the tap on full, more water flows in, more charge flows into the capacitor, it takes less time to charge. So in this case, because the resistance is greater, the current gets smaller, and therefore it takes longer to charge. C, suggest an alteration that the student could make to this circuit to increase the maximum energy stored by the 47 microfarad capacitor. Well, as we know, we have this variable power supply, which runs from 0 to 12 volts. It was originally set to 6 volts. Now, what is it that affects the energy stored in the capacitor? Well, the energy stored in the capacitor depends on how much charge is in the capacitor. And the amount of charge that's stored in the capacitor is determined by how much capacitance the capacitor has and how much voltage there is pushing the charge into the capacitor. And as we're not changing the capacitor value, the only thing that we can alter is the supply voltage. So we increase the supply voltage. Part D, the use of analogies from everyday life can help improve the understanding of physics concepts. Vehicles using a car park may be taken as an analogy for the charging of a capacitor. Use your knowledge of physics to comment on this analogy. So, in the picture you can see cars entering from the left-hand side there over a speed bump and taking a space in the car park. They can then leave by exiting through the lower opening in the car park and back out. So, there are a number of things we can say here. Then there are a number of ways that the car park analogy is very similar to a capacitor. The car park itself is like the capacitor. The capacitance of the car park is determined by the number of spaces. The cars represent the charges. The current is represented by the rate that the cars enter or leave the car park. The speed bump represents a resistor restricting the flow of cars. And much like in a capacitor, the fuller the car park becomes, the less rapidly cars can enter. So if we have a graph like this of current against time for a capacitor, it would be the same for a car park. Number of cars entering against time would get less as the as the car park filled up. However, there are some ways that this analogy is not similar to a capacitor. Firstly, in this analogy, the cars are entering and leaving in a clockwise direction. They're entering through that top opening and then leaving through the bottom opening. In a capacitor, the current does not flow in a circuit through the capacitor. The current flows in and charges the capacitor and then flows out as it discharges in the opposite direction. Also, in a capacitor, the amount of charge that is stored in the capacitor can be increased by increasing the supply voltage. In this analogy of the car park, there's nothing that represents the supply voltage. We would have to imagine that there's some force forcing extra cars into the car park. So once it's full, you've got some sort of crushing machine that squashes the cars and lets more cars in. And that's not really realistic. So there are a couple of ways that analogy is not similar. If you were answering this as an open-ended question in your exam, obviously you wouldn't want to write as much as I have here. I wrote down all the things that I could think of that made the analogy work or not work. But to be able to show a good understanding of the idea, you wouldn't have to recite all of that, obviously. Question number 14. Solids can be categorized as conductors, insulators, or semiconductors, depending on their ability to conduct electricity. Their electrical conductivity can be explained using band theory. The diagrams show the valence and conduction bands of three solids, X, Y, and Z. One represents a conductor, one represents an insulator, and one represents a semiconductor. So there you can see a diagram of X, Y, and Z. And in X, the gap between the valence and conduction band is very large. Y, the gap is much smaller. And in Z, there's no gap at all. In fact, the two bands overlap to some extent. So, which one is a conductor, which one's a semiconductor, and which one's an insulator? Well, X is an insulator because there is a large gap between the valence and conduction band. That means that electrons in the valence band are unlikely to have enough energy to move into the conduction band, and therefore conduction is unlikely. Y is a semiconductor because the gap between the valence band and the conduction band is small. So although the electrons would normally exist in the valence band, some may have enough energy to be promoted from the valence band into the conduction band, allowing conduction to happen. As temperature increases, more electrons would have that amount of energy, and more electrons would make it into the conduction band. And solid Z, obviously, is the conductor, because there is no gap between the valence and conduction band. So therefore, electrons that exist in the valence band are already existing somewhat in the conduction band as well. And so it is always possible for electrons to be able to flow through the conduction band. Using band theory, explain why conduction can take place in a semiconductor at room temperature. Well, as I just mentioned, semiconductors have a small energy gap between the valence and conduction bands. That means that some electrons will have enough energy to move from the valence band to the conduction band. C. Silicon can be doped with arsenic to produce an N-type semiconductor. State the effect that doping has on conductivity of silicon. So here's a little animation to explain that. So these black dots, they represent the silicon nuclei. The red dots, the electrons in the silicon. And what happens is the silicon shares electrons with its neighbors so that it has enough electrons to fill its outer energy level, and therefore is an insulator. However, when we add arsenic has 5 electrons in its outer shell, so it shares its 5 electrons with the 4 silicons around about it, giving it 9 electrons in its outer shell, which is 1 too many. So that one spare electron gets hoofed out of the valence band And where can it go? Well, it can go into the conduction band, and it's able to then flow around the circuit. So by doping the silicon with arsenic, we increase the number of free charge carriers. And increasing the number of free charge carriers will mean that the conductivity of the substance will increase. D. Resistivity is a measure of a material's property to oppose the flow of charge. The resistivity of silicon is 2.3 times 10 to the power of 3 ohm meters. The resistivity of copper is 1.7 times 10 to the power of minus 8 ohm meters. Compare the resistivity of silicon to the resistivity of copper in terms of orders of magnitude. So, orders of magnitude are the times 10 to the power ofs. So, silicon is of the order of times 10 to the power of 3. Copper is of the order of times 10 to the power of minus 8. So what's the difference between 3 and minus 8? Well, that's a difference of 11. So the resistivity of silicon is 11 orders of magnitude greater than copper. And that brings us to the end of these electricity questions from the 2019 paper. I hope that was helpful for you and you got something out of this. So I will speak to you again another time. Goodbye for now.